Today I'm going to talk about PV system failures, temperature and installation effects. Here's a brief outline of the talk. After the motivation, we'll talk about fleet performance of about 100,000 PV systems in the US, hardware problems and installation quality effects, and finally failures and climate effects. As motivations, I'll take a single graph. It's the global cumulative installed capacity from the 1970s to 2019. And you can see the exponential-like growth curve. You can easily calculate the percentage of systems installed for less than 2 years. It was as high as 70–80% in the early days, went as low as 20% and rebound to about 40–50% today. (70–80%) in the 1970s and early 1980s was fine because warranties, now shown in green on the far right axis, was about 2–3 years. But then warranties increased to 25–30 years that we have today. But we still have about 40–50% of all systems installed for less than 2 years. And this gap, reliability, needs to bridge this gap between what we know from the field and what we guarantee. And this is why a data set, as I'm going to show you today, is so important, because it gives a high-level overview of the state of the industry. 1603 data comprise about 100,000 PV systems, totaling up to 7 gigawatt system capacity. At the end of last year, there was about 7% of all systems in the US. For 60,000 of these systems, we have 5 years of production data. We have 400 to 500 utility scale systems. So it's overall a good representation of the overall US market. What we have is annual production data. We have the location, predicted production, the size, but for most systems, we do not have mounting configuration. We also have comments regarding the performance, and through our collaboration with Lawrence Berkeley, we have monthly production data, mounting and module information for systems greater than 5 megawatts. So in the first section, we'll look at the overall fleet performance. For systems greater than 5 megawatt, we have also the DC and the AC rating of the system, so we can calculate what the DC-AC ratio is over time. That's shown in this graph, and it's color-coded by the capacity, the size of the system, and it's symbol-coded by the type of mounting. As you can see, the DC-AC ratio has been going up consistently over the last 7 years. That is important because that can lead to inverter clipping. That is, during the most productive times of the day and year, the inverter limits the PV production. But it's also interesting to note that not all utility scale systems installed are one-axis tracked. Some of them are still installed as fixed tilt systems. So how's the overall fleet performance? What's shown on the left is the measured over predicted ratio as a cumulative distribution function for all normal systems. That is, systems that have not knowingly been impacted by some kind of issue, like a hardware issue, for example. And it's color-coded by the size of the system. So residential systems we have categorized from 1 to 25 kilowatt. We have commercial systems from 25 kilowatt to 1 megawatt in blue. And we have utility scale systems larger than 1 megawatt in green. You can see at the P50 that most systems perform as expected or slightly overperform. But at the P90, you can see that 80–90% of normal systems perform within 10% of the predicted production or better. These numbers are very similar to an independent study by Fitch that was published by Green Tech Media earlier this year. They found 86% of systems performed within 10% of the P50. You can also graph all systems that have known issues. And of course, they don't perform as predicted at the P50, but it's interesting to note that residential systems in red are more impacted than commercial or utility scale systems. And we will talk about this later. So in the next section, we'll talk about more in detail about hardware problems, installation, and quality effects. This graph shows an itemization of all hardware issues. On top is shown the occurrence as a function of year from year 1 to year 5. But because there might be problems with the annualization, we don't know if all systems performed for the entire year. We also rolled it up to 5-year means, and that's shown in filled symbols. It's color-coded by the size of the system into a residential, commercial, and utility system. At the bottom is the estimated lost production due to a specific hardware issue. So we look at if a hardware issue has impacted the production in a certain year, and then we look at the preceding and subsequent year, determine whether its production was normal, and then we can estimate, it's a rough estimate, to what the impact is on lost production. So let's look at these categories in more detail. The highest occurring issue is inverters. That's not a surprise. That has been found in several studies before. A little bit of a surprise is that meter problems are also fairly high up. We can look at exactly what happened to inverters and meters. In most cases for inverters, we do not know why they failed and what component failed, but in cases where we do know this is shown on the left-hand side. For most of these cases where we do know, it had to do with the data collection and shown in dark blue. But there are also some specific hardware components inside the inverter that were shown to fail, such as fuses, fan capacitors, control boards, especially for smaller residential inverters. On the right side is shown the same graph for meters. And 3/4 of those issues were actually caused, or actually happened to be failures that led to replacements. You can also see that year 1 and year 2 has a higher occurrence than later years, pointing towards possible startup issues. The next two categories are other repairs or unspecified repairs and maintenance events. Maintenance events don't occur quite as often as other repairs, but when you look at the lost production at the bottom, they typically don't have as high of an impact as repairs. And that goes into the whole debate about that proactive maintenance has less of an impact than reactive repairs, which is not limited to the PV industry. It's a very general topic. The next three categories are breakers, fuses, and wires. And those issues, especially wiring issues that occur more frequently in the first 2 years, especially undersizing wires, point towards installation quality and best practices that could be improved. We also show tracker and microinverters, though because we don't have mounting configuration for all systems, we probably most likely underestimate the numbers shown here because not all utility scale systems are one-axis tracked, as I shown earlier, and not every residential or commercial system uses microinverters. Next, module and string issues. Module issues occur not quite as frequent, 0.2 to 0.02% per year, but it may not capture all underperforming modules. String issues are typically caused by strings connected backwards, so they wouldn't produce. And finally, the evil twins, as I call them, on the far right-hand side, ground faults and connectors. Connectors are specifically MC4 connector issues that were not properly crimped and started to pull apart. And that could be a safety hazard as shown in the next slide. And what you can see here in this video are not two MC4 connectors, but two electrodes that are being pulled apart. And that's during the day under load on a 1 kilowatt system, and you can see there's an arc forming. So connectors, especially ones that pull apart, are a fire risk, a safety hazard, and despite the fact that they don't occur very often, they deserve our full attention. Some comments were detailed enough that they not only specified what broke, but also when it broke and when it was fixed. So that allowed us to summarize how long it took to repair issues for specific items. So for example, inverters on the far left, you can see we have data for all categories. That's not for all these categories, but for inverters on the far left, when you look at the box plot at the median, it took about 6 days to fix inverter problems. It took a lot longer for commercial systems, more like 3 weeks. And when you go to residential systems, it took more than a month. And that is very important for apparent performance loss, which is shown on the right-hand side. Let's pretend we didn't know that inverters were down, but use the production numbers from each of these systems to calculate an apparent performance loss rate. Because inverters for utility systems were down only for a few days, there's no apparent performance loss. But because inverters for commercial and residential systems were at the median down for much longer, there's a clear apparent performance loss, but it's not a real performance loss. And that's very important to differentiate between non-recoverable versus recoverable degradation. When we look at maintenance issues, like inverters were down, that are recoverable degradation, and they can imitate non-recoverable degradation. That's very important that we are aware of this, especially when we evaluate system performance versus module performance. Some of the issues, as I pointed out before, like wires, breakers, ground faults, and so on, pointed towards installation quality issues. What's shown here is the number of installers as a function of systems installed per installer, and it's color-coded by system size. And you can see the big residential and commercial installers. They are on the far right of this axis, where one installer might install thousands of systems. But on the far left, there's a large number of installers that install only 1 or 2 systems. And the question is, does that lead to an increased hardware problems? And that's shown now in the black diamonds. And you can see the installers that installed only 1 or 2 systems do tend to have higher occurrence of hardware issues than installers that install many systems. So practice makes perfect, but it also points toward that installation certifications, for example, through IACRE or installer training, could be beneficial and has a positive impact on long-term reliability. So in the last section, we'll look at failures and climate trends. However, we don't use the Köppen-Geiger scale for climate because that was developed for agricultural purposes. Instead, we're going to use PV-specific climate zones developed by Lawrence Berkeley and Sandia. On the right is shown all the hardware issues lumped together. And you can see there's a clear and significant trend for utility scale systems with higher failure rates occurring in hotter temperature zones. But you don't see that similar trend for residential and commercial systems. There's a similar pattern for unspecified repairs and breakers, although there may be a slight trend for commercial systems here. But again, for inverters, there's a very clear trend and significant trend for utility scale systems with higher failure rates in hotter temperature zones, but no such trend for residential and commercial. And so the question is, of course, why is that? To answer this question, we need to look at the type of installation. On the left is shown a typical utility scale systems where you can clearly see the inverters. But it may be different for residential and commercial systems because it may depend on the orientation. So on the right-hand side are two examples. These are inverters from the same manufacturer and the same type of inverter from about the same location and a moderate temperature, so on number 3. But because in the middle, the inverter is located on the north side of the residency, there are no failures in 5 years. On the right-hand side, however, because the inverter is located on the south side in the northern hemisphere, so they're exposed all day to the sun, there were 3 failures in the same time span. And that points towards that more shade is really beneficial for inverter performance and long-term reliability. We also looked at all the systems that did show inverter failures and summed up the orientation of the inverter and the location. And that's shown in these orange bars. And you can see that those inverters tended to have higher percentage towards the south and the west than the east, and almost none of these inverters facing north. Also, if there was a possibility of shade, for example, through an adjacent structure or vegetation, we showed this by cross-hatching it. In comparison, we took a random sample from all the systems that did not show any inverter failures because we couldn't look at all systems. We took a random sample, and that's shown in blue. And you can see the orientation of those inverters is kind of evenly distributed across those orientations, maybe with the exception of the southern orientation, that shows actually a little less. Again, there's a crosshatched of possibility of shade, and you see there's more possibility of shade than the systems where you had failures. You can also see this in this example here. These inverters were actually oriented towards the south, but the way the modules are mounted above the inverters, they're actually providing some shade in the middle of the summer. So southern location in the northern hemisphere is not the best because you're exposing the inverters to sun and heat all day. But sometimes there is no other choice, but then there's other possibilities to shade them through the mounting on awning or something like that. Meter issues didn't show a lot of strong trend with the temperature, but it showed a clear trend with higher humidity, more failures in higher humidity zones than in lower humidity zones. Modules and microinverters didn't show a particular climate trend, and that might have to do with the details of the mounting that is important. Like, for example, if they're mounted on a roof, how far above the roof they're mounted, which I talked about in my presentation from last year. Finally, trackers. There's a slight correlation with higher failures in hotter temperature zones, but we clearly need more data for this. But there's a much clearer and significant trend with higher failures in higher wind speed areas, and that's probably not a surprise. So in conclusion, a little bit of a mixed message. There were some positive signs. We didn't see any widespread failures. Most systems performed as expected, so 80–90% were within 10% of predicted. Module failures were pretty low, but may not include all underperforming modules. But there were also some clear warning signs that I think we as a community need to take seriously. Inverter failures were pretty high and might have been correlated with some of the best installation best practices. Shade really helps. In general, installation quality can have a significant impact on long-term reliability. And finally, there are some good things that we saw at the utility scale systems, but in general, I think strengthening a more proactive approach as opposed to a reactive approach to operations and maintenance will really make a difference. And with that, thank you very much for your attention.